many years ago.
Hmm.
So a long time ago. I think I left there 20 years ago, actually, computer science, 23 years ago.
Oh, I see, right, yeah. The biography I've got seems to talk more about IT.
Does it? Oh.
Does say what your research interests are. Do you still do any research in the background?
Yeah, I do. And my main research is astronomical polarization, pulsars, and so on. So I don't know if that's in the biography. I sent something to whoever contacted me.
Pulsars and power, yes. Yeah. The other thing I know is Galway got some kind of contract or deal on with the ELT, didn't they?
Yes. What happened there is that we've been working quite a long time through Opticon. I was a board member of Opticon, and we had a very big meeting in Galway, 2014, 2015, which got a lot of very good coverage on RTE. And I think that triggered some thoughts about joining ESO. So we actually had, sort of a little bit of a push in that direction. And spinning out of that, Nicholas Devaney, whose work on adaptive optics caught people's attention in Maori and things. So at that point, he then joined the Maori consortium once Ireland joined ESO. And he has guaranteed time on the ELT. So it's
great. Wow, guaranteed.
Now, I don't know how many nights he's got, probably about 3, I think, which is quite an achievement in itself.
39 meter telescope, wow.
Well, yeah, so I'm not quite sure how he's going to divvy it up, whether he's going to open up a sort of little core or he's just going to use it for his own exoplanetary research. We'll see. So, yeah, it's quite an achievement. And, yeah, he's working on Maori. But he was also working on LISA as well. He did some active optic work on LISA. So that's a good NUI Galway contribution from the School of Physics.
Yeah. I hope Anne's listening because that'll be going in the magazine.
Yeah. Okay.
I've got a very small screen.
What I can do is give you his contact details and he can tell you more about that. I'll mention some of this as we go through it.
Great. Well, the numbers are rising. I say we're up to 36, which is very good.
Very good.
50% up on last month.
That's very nice
to see. People are still being admitted. 37, there we go. So what time are we at now? 2 minutes past 7. So everyone can probably hear us, which is good. We'll start, let's say about 5 past, give a few people a chance to find their way into Zoom. And I need to shut down one thing here. Oh, I get my notes up on a bigger screen. Laura, you can probably hear me there, yeah?
Yep.
Are you going to start the recording or will I?
I can start it when you're ready.
Yeah, and you're going to collate questions in the chat box, yeah?
Yep.
Okay. Close to ready to begin. Oh, you don't need to start the recording yet. You're the host, I assume. Am I a co-host or what way you're working?
Yeah, you're a co-host.
Oh. Am I just signed in as Astronomy Ireland or David Moore?
Astronomy Ireland.
more person trying to get in. And, right, seconds away. Okay, 7:05. I think what we'll do is we'll let you start the recording. Right, well, good evening, ladies and gentlemen, and thank you for joining us from all over Ireland. I've been watching the bookings coming in from Donegal all the way down south. I think we even have 1 or 2 international attendees watching us today, which is great to see. We have a fantastic talk for you this evening with Professor Andy Shearer, who's over in NUI Galway. And before that, we'll tell you a little bit about what's been happening since the last meeting, then have our main event, and then we'll tell you a little bit about what's coming up. The big story, of course, being the Perseid meteor shower due to peak in the next couple of days. So stay tuned for that. And at the very end, if you want to ask any informal questions about any aspect of astronomy, a few of us will stay on for a few minutes. So we'll make an evening of it that way. Let me grab my notes here. Yep. My name is David Moore. I'm the founder of Astronomy Ireland and editor of Astronomy Ireland magazine. We were supposed to have our 30th anniversary last year, but things have sort of cut our celebration short. We're still hoping to run some big events, but we're waiting for all these restrictions to ease off so we can enjoy ourselves as we normally do. But the Society was founded in 1990. Relative to population, it's now the world's most popular astronomy club. And we have members all throughout the 32 counties, a few abroad. There's something like 100,000 people or more following us on social media and emails, and that's growing all the time. During the lockdown period, a lot of hobbies boomed, including Astronomy Ireland. We nearly doubled our membership in 1 year, which is more than we've ever done in 30 years. So every cloud has a silver lining. We hope you'll all stay with us. You'll get your magazine every month, Astronomy Ireland magazine. If you haven't already got this, I'll tell you where to get it at the end. It'll tell you loads more about what to see in the sky. A little bit about what we do for any of you that are new. We publish Ireland's monthly astronomy magazine. We also send out a weekly email to just members only, and that reminds you of what's happening in the sky, gives you any new stories that are coming up, and tells you about various events like these lectures and other events as well. By the way, if you've missed one of these lectures, they happen every month, usually on the second Monday of the month, and they're available on DVD going back over a decade now. You'll see details of that on our website, astronomy.ie. But another big thing we do, as well as the monthly lectures, is we have evening classes that also run online twice a year. They're enrolling now for classes beginning in October, and they'll be usually it's end of January, early February when they're run again. So watch out for those if you want to take the hobby even more seriously. Back in the day, when we could all get together physically, we had lots of watches where we'd set up telescopes and invite people to come and view the moon, planets, eclipses. We managed to do a very brief one in June for the eclipse, but numbers had to be restricted. We didn't promote it like we normally do, and we've had thousands of people at some of these events. But we do have our big event coming up, which I'll just mention briefly now, given the restrictions. That's our Starbecue, Ireland's biggest annual star party. It's a barbecue under the stars in the dark skies of Wicklow. We take over the GA grounds up at Roundwood, which they kindly rent out to us for the night, fill the pitch with really powerful telescopes, thousands of times more powerful than your eye. We also have talks in the hall as it's getting dark, and a professionally catered barbecue outside in the evening as well. It's a fantastic event. We've had up to 600 people at it in the past. We're still waiting to find out if the GA are opening up their premises to external groups yet. The powers that be haven't yet decided. everybody's watching out for the restrictions ending. So as soon as we know, we'll be announcing that on our email list to the members. But also, you should follow us on social media, Facebook, Twitter, Instagram, because that's where we'll announce late breaking news like that as well. We also do talks in schools all around the country. We've even been doing some of them like this on Zoom online. And we have a huge media presence. We're on radio today, for instance, talking to the journal.ie as well today, getting ready for the Perseids. And that helps to keep the society as big as it is. So that's a bit about what we do. What's been happening? Well, our last meeting was our July lecture. It was on the 12th of July when Brian Harvey, who's an internationally acclaimed space author, he's had about 5 or 6 books now to his name, but lives in Dublin and has been a member of the club since the very beginning 30 years ago. His latest book is about European and Russian cooperation in space, just out this year. And that's what he gave a talk on. And you can imagine somebody who researches an internationally acclaimed book like that knows his stuff. So very informative. And if you've missed it, you can still get it on DVD. And usually within a month or so, we still have it online as well. So you can watch it that way, contact the society afterwards. So a big thank you to Brian Harvey for giving our July lecture. The news around that time, of course, was that Richard Branson had just gone into space. And then we were telling people Jeff Bezos was about to go, which he did successfully. And you'll see more about that in the next issue of your magazine. In sort of astronomy news, I'm going to tell you briefly what's in the sky after our main speaker. The main thing is planets Jupiter and Saturn are now in the evening sky. Venus is very hard to see low down just after sunset. We had the International Space Station in the last month, but now it's gone out of evening skies. It won't be coming back to Irish skies until August 27th, and that will be before sunrise. So you're going to have to wait till September if you like watching it in the evening sky. Another event that we alert you to yesterday was that the BBC Sky at Night programme. We've had practically every presenter from the Sky at Night come to Ireland and give a public lecture for us. That was on BBC 4 last night around 10 o'clock, but it will be repeated if you missed it this Wednesday at 10 to midnight. And the subject this month is the Juno spacecraft that's orbiting Jupiter, which you can see in evening skies. Jupiter is, not Juno, it's small compared to Jupiter. So another busy month with billionaires going into space and all kinds of other shenanigans happening as well. But that brings us to the main business of the evening. We're going to take questions in the chat box. So if you have any questions as you're going on, just pop them there and we'll collate them together and ask Andy at the end of the talk. But let me introduce our speaker. As I said, we're delighted to have Professor Andy Shearer. He started off in Durham University, where he got his PhD in cosmic ray physics. He then worked for a while in Bristol University and in industry as well, before he took up his position in the physics department at University College Galway, as it was known back then, in 1991, just a year after Astronomy Ireland was formed. Then in 96, he was appointed a lecturer in the Information Technology Department, then renamed National University of Ireland, Galway, where he's retired at the moment from there, but is located in Galway at the moment. But in 2005, he founded the Irish Centre for High-End Computing and was its first director. His research interests will cover high-performance computing, grid computing, medical and astronomical image processing. He's been modeling astrophysical plasmas and high time resolution astronomical observations. He has a specific interest in optical observations of rotation-powered pulsars. His group is credited with the discovery of optical pulsations from 2 out of the 5 of the known optical pulsars, which is a great feather in the cap for Galway, indeed for Irish astronomy. Over the past 20 years, though, he's also been involved in lots of public engagement and outreach events like this evening tonight. He's got a very fascinating topic. I think things are dramatically going to change over the next decade with some incredible leaps in the advances of telescopes, both optical, radio. Things are really going to blossom in the next decade. It's going to be a very exciting time. So I'm going to invite Andy to give us a talk on that subject. Thank you very much, Andy.
Great, thank you very much for the introduction. So I hope I can share my screen. and I hope everybody can hear me.
Yep, we can.
We share screen, and hopefully, I hope you can see that.
Yes.
Yeah? Yep, good. Okay. As I said, thank you, David, for that introduction. The title tonight is basically talking about the next decade of astronomy. And when I agreed to give this talk, I thought, well, that would be quite interesting. There'll be a number of satellites and new ground-based facilities will come on stream. What I hadn't realized and hadn't counted for is the number of new facilities and so on, which will come on stream. So this will be very much a whistle-stop tour of the next decade to actually see what we can actually do. And I'm going to break this down into essentially asking what are the kind of questions which we need to have some answers to, i.e. what don't we know? And hence the reason and the rationale for launching a lot of new satellites and also some new ground-based facilities. I will also talk a little bit about what influences what influences astronomical discoveries. And that will be basically a little bit of history. So those people who are not interested in history, I apologize in advance. So there'll be some history in terms of how technology has actually aided our understanding of the universe. And during the talk, I'll also try and concentrate a little bit as well, and I'll mention where there is an Irish input into a lot of this work. So we have a number of groups in Galway, which has been mentioned, who are making a contribution to these. DIAS are making a very significant contribution, Trinity, DCU, and UCD as well. So there is a big kind of trans-Irish contribution to astronomical development, primarily through European Southern Observatory, which I am now a member of, and the European Space Agency, which we've been a member of now for many years. Okay, so basically, will the next decade answer all the remaining questions, or will it create a lot more? I seriously hope it will create a lot more questions. That's always more interesting. The images which I'm showing is on the left-hand side, the current workhorse of the of kind of space-based optical astronomy, which is the Hubble Space Telescope, which was launched in the early 90s. And that is continuing, and it's continuing to still make dramatic discoveries. So it's still an extremely important instrument. On the right-hand side, what we have is the James Webb Space Telescope, which will be launched hopefully this year. There's often been sort of some problems in its launch date, but I think we're coming up to quite an imminent launch. The video here is an animation which I first saw a few years ago when we had a meeting about all the next kind of technological developments which are coming up in Galway. And the PI of the James Webb Space Telescope showed this movie, which he described as his 2 weeks of terror. And the reason being is that when the Space Telescope is launched, it has to fit in an existing rocket. And the Hubble Space Telescope is about as big as you can actually launch into space without having to do something clever. The mirror on the Hubble Space Telescope is about 2.5 meters across. The mirror on the James Webb Space Telescope is 6.5 meters across. So in order to fit it into a rocket, the mirror has to be folded up. And then this, rather than being in a low Earth orbit like Hubble, and those people who might have seen the film Gravity, it started off with the repair of the Hubble Space Telescope from astronauts. That's possible because it's in a low Earth orbit. The James Webb Space Telescope, because it's an infrared telescope, will be about 1 million kilometers or so away from the Earth. So it's going to take 2 weeks to travel there. And whilst it's traveling, it's unfurling. And you can see here in this animation the complexity of everything which is unfurling in those 2 weeks. And the terror aspect of this, as far as the principal scientist is concerned, project scientist is concerned, is that most of this technology has never been tried in space to do this. There's never been a mirror of this size opening up. The bottom of the telescope is this kind of shield to protect this telescope from the heat from the sun. It's going to be an interesting 2 weeks, and this shows you the position. It's known as the second Lagrangian point away from the Earth, about 1.5 million kilometers away from the Earth. Okay, so that's basically one of the telescopes we'll be talking about. I love this quote. It's one of my favorite quotes, and I think I might have shown it to Astronomy Island maybe 5 years ago. But it basically, whatever you might think of Donald Rumsfeld, who died recently, he came up with this quote for which he was ridiculed, and I thought it was a bit unfair. There are plenty of other things he could have been ridiculed for. But he came up with this, and he talked about known knowns, known unknowns, and unknown unknowns. And this, to me, described fundamental science, and particularly the known unknowns. That's basically research into things we don't know about and would like to know about. And then quite often we trip over unknown unknowns, and that's quite often the interesting bit. So in some ways, the next decade will basically be talking about the known unknowns and the unknown unknowns. So what don't we know? What are the questions which we need to answer? We don't know anything about the dark universe. We don't know what dark energy is. We don't know what dark matter is. I'll describe these in a few minutes. We don't know what was the nature of the first stars which evolved in the universe just after the Big Bang. We don't know when the first galaxies started and what form they took. Another thing we don't know, is there life elsewhere in the universe? Can we detect life in the solar system or around other stars? We have a pretty good idea that it's there. I read a book a few years ago, which was Things I Know Which I Can't Prove, written by a number of different scientists. And one of them, I think it was by Martin Rees, was that he basically knew there was life elsewhere but couldn't prove it. And I think that's the general view which astronomers would have, is that there should be life elsewhere, but it's very difficult to prove. And that's the aim of many of the missions in the observatories, which I'll be talking about, is to see if we can detect either the conditions where life could exist or the direct detection of the evidence of life around other planets. For example, oxygen or chlorophyll would be a good indicator that there's life. And there are many more things. There's things, fast radio bursts, which we've been involved in trying to observe. These are flashes of radio emission which just occur for a few milliseconds and then die away. And no one knew what they were. And more recently, there have been some observations which have indicated that there are two types. One type is possibly coming from the merger of two neutron stars, and another type is a flash of radio emission from a type of neutron star called a magnetar. But there are many more areas of astronomy and astrophysics where we're actually not quite sure what they are. And these are the kind of known unknowns, if you like. So basically, if we can't answer the questions now, how can we answer them in the future? What do we need to do? Do we need better astronomers? Now, as an astronomer, I like to say no. We've got a pretty good selection of astronomers, excellent astronomy training. We've got very good career paths for astronomers at the moment. Or do we need better telescopes? And that's the main concentration of what I'm going to be talking about. Or do we need better instruments? And really what we need is both. Or do we need different telescopes? And some of the most interesting discoveries come from not the existing branch of a kind of astronomy, optical astronomy or whatever, but through new ways of observing cosmos, gravitational waves, neutrino astronomy, and so on. So all of these, we actually need better telescopes and different sorts of telescopes. First of all, I just want to go through more detail some of the things we don't know. A lot of people might talk about the Hubble constant, which is a measure of how fast the universe is expanding. And it also gives an indication of what the age of the universe is. And the universe is basically is expanding rapidly from the Big Bang. And a measure of the rate of expansion is something called the Hubble constant. I know when I was initially taking astronomy courses in the 1970s, one of the lecturers came up and said that the age of the universe is increasing with time, which was a strange thing to say, but what he meant was that the value of Hubble's constant is changing with time as people make more and more accurate measurements. Now, what we've got at the moment is a problem. We've got something which is called the Hubble tension. The value of the Hubble constant, which is measured locally, and I'm using the term locally to be in inverted commas, we're talking about in nearby galaxies, compared to the measure of the Hubble constant when it's measured using the cosmic microwave background, is different. And what we've got here is a little plot which shows the values going from the year 2000 roughly. We had this value using Cepheid variables, and these are a type of star, an evolved star, which is basically expanding and contracting, expanding and contracting. And an American astronomer, Henrietta Leavitt, in the early part of the 20th century, noticed that the magnitude of the star related to its period of oscillation. So if you can measure its period of oscillation, you would then know how bright it should be and how far away it's going to be. And this is the classic way in which the distance-to-distance galaxies is being used. And in fact, it was one of the main rationales behind the Hubble Space Telescope. And it was one of the first results which came out of Hubble was the distance to a number of different galaxy clusters. And what's happened over the last 20 years is that the value of the H0, the Hubble constant, as measured by Cepheid variables, has changed, has become more and more accurately defined. And this is then compared with the measure of the Hubble constant using the cosmic microwave background, using the microwave emission, which occurred just after the Big Bang, 300,000 years after the Big Bang. And that has become more and more accurately defined. The problem is that, but they become more and more accurately defined, and they have different values. And it seems to be that if you measure the Hubble constant close to the Earth or near to the Earth in the local area, it's different to the value which you measure when the universe was very young. There's been another technique which was to look at it, called using basically flaring giant stars, and that has now managed to come up with a value which is intermediate between the two. So it hasn't really solved the problem. So there's a lot of interest on this particular plot to see whether this is actually real statistical anomaly, or do we need some better astrophysics, or do we need some better physics to actually explain what's going on? So this is one of the serious problems in cosmology. And the other two problems are we don't actually know what dark energy or dark matter is. Dark matter, here's a nice image of the bullet cluster, which shows the distribution of normal matter. This is basically just gas, intergalactic gas, and dark normal matter. And this distribution has been seen using a technique called gravitational lensing, which is one of the predictions of general relativity, that a nearby large amount of matter will distort the images of galaxies which are behind them. And when you look at the distortion in this region, it indicates there's a lot of matter there which we can't see. And similarly, in this region, there's a lot of matter there which we can't see. But in this region in the center, it just appears to be hot intergalactic gas. So this is an indication that dark matter exists, but it's not clear what it is. It doesn't seem to be normal matter. There's also evidence of dark matter from the way in which galaxies rotate. So there are a number of missions which are going to be going ahead to actually look and see whether we can detect dark matter and find out what dark matter is. What else don't we know? I've got a list here, and notice down here, I've got ... because there's lots of things we don't know. And I divided these into three different areas. What we don't know, but we know where or how to look for them. And one area which we need to look at is Earth-like exoplanets in the habitable zone, which I'll talk about that in a minute. It's basically planets like the Earth in an area where it's nice and warm and temperate and life can exist. So we know where to look. We look at stars which are like the sun, and that would be, a very good starting point. Fast radio burst counterparts. There's been a number of different surveys, particularly the CHIME survey in Canada, which has detected thousands of these fast radio bursts, some of which repeat. And because they repeat, you can actually begin to work out which galaxy they come from. So initially it was thought they might be local, or they might be at cosmological distances, and it's been indicated that there are cosmological distances. So it's an enormously strong burst of radio emission coming from the edge of the universe, or near the edge of the universe. But we can detect the galaxies and look at those galaxies for those ones which repeat and discover the conditions around them. And they seem to be associated with galaxies which have young star-forming regions. So that maybe indicates something that it's actually related to massive stars which have evolved. Ultraluminous X-ray sources. These are X-ray sources which are much brighter than they should be. And it's not clear what they are, but it's probably related to some jet phenomena where material accretes onto something like a black hole, and you get emission coming up like a jet. The other area, which is terribly exciting at the moment, is the counterparts to gravitational wave sources. We've had the Nobel Prize for Physics a few years ago was awarded for the detection of gravitational waves. What we need to try and find out is what do the sources, what are the progenitors of gravitational wave sources look like? And normally they're quite large black holes with masses of a few times the mass of the sun. Or in one case, it's been a black hole and a neutron star which coalesce and give out gravitational waves. Counterparts to high energy neutrino sources. There are neutrino experiments. I'll describe the ice cube experiment in Antarctica later on. And one neutrino has been definitely identified as being coming from an extragalactic source, a blazar, which is an active galaxy. And there are many other things where we're not quite sure what they are, but we know roughly where to look at. There are things which we don't know where or even how to look for them because we don't know what they are. Dark energy and dark matter. And there are lots of different ways in which this can be looked at. Dark energy is a significant problem. It contributes, it's about 70% of the energy budget of the universe is in the form of, or seem to be in the form of dark energy. And this is the energy which seems to be accelerating the expansion of the universe. So this is affecting the rate at which it's expanding, and it seems to be increasing at the moment. Now, there are two possibilities here, is that one, that it exists, and then maybe our physics isn't correct, or our astrophysics isn't correct in terms of what the scale of it is going to be. So that's been looked at. So even experiments like CERN with the Large Hadron Collider are beginning to investigate the dark universe to see if they can see evidence of dark energy and dark matter. And dark matter is this material which we can't see, but we know it's there. But we don't know how to look for it. We're not quite sure whether it's exotic particles, or could it be that our physics, the general relativity, has some issues related to it which needs to be modified. I personally would regard that as unlikely for dark matter, but possible for dark energy. Then there are things we know where to look, but not sure. This actually goes back to my PhD 40 years ago, the origin of ultra-high energy cosmic rays. And these are charged particles which are continually bombarding the Earth. Some of them have ridiculously high energies. So down here, we have these extremely high energies. The energy here is in what's known as electron volts. This is 10 to the 20, that's 10 with 20 zeros after it. By comparison, light has an energy of about 1 eV. So this is extremely energetic particle. It's the same energy roughly contained in a heavy shoe being dropped from the height of about 2 meters onto the ground, all in one charged particle, and probably a proton of these kind of energies. Now, it's not sure where these are coming from, but the likely candidates are pulsars or possibly active galactic nuclei, but some kind of form where there are astrophysical shocks are probably responsible for this kind of acceleration. But even down here, there are significant problems of physics trying to explain them and how they can traverse the universe, because they should interact with background radiation. So here are all these kind of things which we don't know. And luckily, the funding agencies have decided that these are sufficiently important problems that they're prepared to spend quite a lot of money to actually try and solve them. In more detail here, the fast radio bursts. I show this slide because a nice picture of the CHIME radio telescope, which is about unusual. We don't know what they are, but I show this one because to indicate a kind of Irish link to this. We have, I spent 2 weeks trying to observe a repeating fast radio burst using our polarization instrument down in the south of France. It was a very nice 2 weeks in the south of France, but unfortunately this repeating fast radio burst, which is also being observed by a large number of telescopes around the world at the time as part of a big campaign, refused to repeat during the campaign, which is a bit unfortunate. But later on, last year, this paper was published when a galactic magnetar was observed to flare in the way in which give a fast burst of radio, just in the same way as we've seen these in extragalactic causes. And Greg Hallinan here, who's one of the PhD students from Galway, who's now an associate professor in Caltech, was one of the co-authors. So here's someone who started in Ireland and is now quite a significant astronomer in Caltech in California. Habitable zone. And here we see next question, how many Earth-like planets are there? That's another question. And here we see something, a little animation from the Kepler telescope showing the habitable zone. If we compare it to the solar system, Venus is on one edge of the habitable zone, Mars is on the other, and the Earth is right slap bang in the middle. So what we find is that around different stars, we will have a habitable zone which is smaller smaller around a hot star compared to a red giant star. Sorry, the other way around. So depending on the temperature of the star, we'll have a habitable zone which extends over different distances. Okay, how do you make better observations? I asked whether we need better astronomers and dismissed that because we have exceptionally good astronomers at the moment. Do we need better technology? And the answer is yes. We need larger telescopes. We need more efficient detectors. We need new detectors. And we need new messengers, neutrinos, gravitational waves, and maybe unknown messengers. And by messenger, I mean something which gives us information about the cosmos. What we have here is the two types of telescope which are being on the bottom here. We see Euclid, which is going to be launched soon, which will be examining primarily the search for dark energy and dark matter. We see Plato here, which will be launched in the middle of this decade, I think, which will have, which is looking for exoplanets. And here we see the biggest European project currently going on, which is the European Extremely Large Telescope project, which is a telescope with a primary mirror, which is 39 meters across. And here we see a kind of an animation. It's not real, it's nowhere near built yet, showing a couple of the engineers as the instrument opens up at night. Its first light is designed to be in 2024, 2025. And what you see here are one aspect of this. The telescope is on the ground in Chile, on a mountain in Chile, and in order to get rid of the effect of the atmosphere, the seeing, the twinkling of stars, which affects all astronomical observations, lasers are used. And here we see the Atacama Desert in the background, and we see kind of flyby of the observatory dome as it will look. And we can then walk into, have a little fly into what the observatory is going to look like for those people lucky enough then to use it. And you see it's very clean at the moment because it's an animation. Normally there would be equipment and so on lying around. And we see the primary mirror. And the primary mirror consists of 900 segments. And we see an engineer here with his hard hat on looking at the instrument. And we see the tubes, which will then fire the lasers into the sky to produce artificial stars, which then the adaptive optics around the instruments will then use to correct the distortions introduced by the stars twinkling. And we have one of my colleagues in Galway, Nicholas Devaney, is working on MARI, which is the instrument designed to make those changes. So it's the adaptive optics instrument on the LT. So that's a nice Irish contribution to this program. So without MARI, most of the telescope operations wouldn't work very well. What we also see is two projects for those people who are currently going to school. And it's LISA, and there's the Laser Interferometer Space Antenna, which is the European Gravitational Wave Experiment in Space, which will be launched in the early 30s. And this is designed to measure gravitational waves by interacting, producing an interferometer in space with these widely separated satellites. Again, more of that in a minute. Another one which I won't describe in much more detail after this is HABEX, which will be launched in the mid-2030s, which is designed to, as a proposal to measure Earth-like planets and to actually direct imaging. And it's going to do this by having a telescope diameter of 4 meters, and 124,000 kilometers away, there's going to be a star shade, which will then block out the light from the star, allowing the instrument then to observe the actual light from the planet. And this is one of the problems of exoplanetary studies, is that the exoplanets, the light from the exoplanet is much, much dimmer than the light from the star, and the starlight tends to dominate it. So this is a way to try and stop it. It's called a coronagraph. So these are some of the possibilities which we're going to be observing now. Okay, a little bit of history just for about a few minutes, just to show how things have changed. If we say one of the best astronomical detectors ever is the one which we have, the human eye. Each blink of an eye is an image of about 500 megapixels, which is much better than any mobile phone anybody's got. It will image at 20 frames per second. You can also see in color. The problem is it's very small. But up to 1609, this was all of astronomy, was basically naked eye astronomy. And a lot of the kind of mythology that's built up in astronomy comes from these naked eye observations. We knew of 5 planets, we knew about comets, meteors, and we knew some of the stars up to a magnitude limit of about 6. So the magnitude limit is about 10 of the faintest star. Early telescopes came in. This is the Galileo's telescope here, with an aperture of 26 millimeters, which is about the width of a thumb. And basically, from 1609 onwards, the 5 or 6 of the 5 planets became 6 very quickly, although Galileo didn't realize he'd actually seen a new planet. But after that, the other planets were beginning to be observed, followed by Neptune and Uranus were followed fairly quickly afterwards. The important difference was that Galileo could see the moons of Jupiter, which caused him a lot of problems, Saturn's rings. The Milky Way was also resolved into stars, and we could see stars which are about 10 times fainter. And that's an important thing, is that you have a big telescope, the aperture was bigger than the eye, we can see fainter. We then have a look at, say, the human eye plus the Burr telescope, which is here. The aperture is 1.8 meters, about the same size as the Hubble Space Telescope, slightly smaller. You can actually see nebulae. I'll show a picture of that in a second. And with the Burr telescope, using the human eye, we actually have about 17, go down to magnitude limit, about 17 or 18 under very good conditions. Sadly, Burr is not necessarily renowned for its very good observing conditions. And what you can see here is a nice little image of someone during the day looking through the telescope, and then you see the light from the mirror, which is down there. That looks very nice there, but you can imagine doing this on a wet November evening. You'll be pretty cold and possibly fairly miserable at this point, unless you're wrapped up warmly. But then, after about 1850, photography came along and expanded our understanding quite dramatically. And here's the technological advance. And this basically introduced astrophysics rather than astronomy. Yeah. So here we see the first known surviving photograph of the moon taken in 1851. And then 12 years later, this image was taken. So in 12 years, astronomical photography went from being absolutely dramatic. The problem previously is, here is a drawing taken, Lord Rosse's drawing of the Crab Nebula. This is why I call it a crab. It looks like a spider crab. You couldn't really record this permanently. That all you could do is look at it and then try and quickly sketch what it looked like. So it relied on drawing and often imagination about what was seen. And here is a more up-to-date picture of the Crab Nebula taken with the ESO's very large telescope. And you can see, yes, he got some things right. You can see these kind of filaments which are here. But what he didn't get right was the overall structure. He had a much more asymmetric view. Then photography, particularly say from Harvard, you can begin to take an image. This is an image of the Large Magellanic Cloud, and begin to look at individual stars and measure their brightness quite accurately. And here's a glass plate. You can see it's cracked. And the size of the dot is indicating the brightness of the star. So you can now begin to actually take an image and go offline and then begin to measure how bright it is and begin to do some astrophysics. You can take different colors. But the important thing is you can begin to analyze these things properly. And it was Henrietta Leavitt who, looking at glass plates like this, discovered the Cepheid period luminosity relationship, which was then used to measure the scale of the universe, and was used by Hubble to measure the scale of the universe. So if we then move on, we went into spectroscopy, and this is where astrophysics really began. This is Fraunhofer's spectrum, and the Fraunhofer lines. This is when you look at the spectrum of the sun, you begin to see these dark lines, and these are indicating of individual elements. And also here's the intensity of light as seen as well. And this allowed us to say that you can actually identify chemical elements. And Bunsen and Kirchhoff in the mid-1850s, 60s and 70s began to identify different elements in the sun. Another one is that here's a spectrum of Mizar, the star, and it showed that the spectrum changed in time. And occasionally this line here, the calcium K line, became double. And this indicated that this was a known spectroscopic binary. So here we had a technology which allowed us now to see things we couldn't see before. That some stars which we saw weren't single stars, but they were multiple stars. So that's one of the indicators that a technology change can lead to a dramatic change in our understanding of the universe. Spectroscopy. And when you look at the spectroscopy of stars, generally, you can see that they fall into different types. And you can sometimes see very complicated spectra, sometimes very simple spectra, and sometimes spectra which didn't have dark lines, but had bright lines. And this confused people in the 19th century, and it wasn't until really quantum mechanics came in, began to explain in more detail what was actually going on, and went to explain what was happening here. So we have astronomical observations which required a change in our physical understanding in order to explain them properly. One of the jobs of the Hubble Space Telescope will be of the ELT, for example, the Extremely Large Telescope, will be to measure the absorption of light from a quasar at different distances. So you've got gas in the way, and we'll see a complex spectrum, and the complex spectrum will have different redshifts corresponding to the different distances which the gas is absorbing. So these dark lines will appear at different points corresponding to the different distances. And given 20 or 30 years observations with the Extremely Large Telescope, way beyond my time, I would imagine, you should be able to directly measure the universe has expanded in those 20 years. So it should be possible to take spectra like this and then go back in 20 years' time and take similar spectra, and you'll see these spectral lines will have shifted slightly. So that's one of the potential results which is going to come out in the next 20 years, is the direct measurement of the expansion of the universe. It's worth bearing in mind that what I've just been talking about is just this small part of the electromagnetic spectrum. And that's what astronomy was until the 1940s and 1950s, when radio waves, Jansky's observations, began to open up the radio universe, and we could begin to see radio galaxies, which we didn't know existed before. Infrared, it was known, even the experiments done in Burr, which showed that there was light which we couldn't see in the red end of the spectrum, which was coming from, in this case, the moon. In the 1960s, 1970s, and 1980s, through various space missions, we began to first of all see ultraviolet light, then X-rays, and then gamma rays. And this opened up a whole new area of astronomy. And if we then combine, for example, my area of interest, which is looking at optical pulsars, they were discovered in 1960s, late 1960s, by Jocelyn Bell, and as a radio object, which regularly beat as the neutron star spins. But they are now known to be very, very strong emitters of gamma rays and X-rays as well. So here you have a link between the different aspects. So in order to understand an object, we need to actually observe it across the electromagnetic spectrum. And then we also have these areas here, these different messengers, cosmic rays, which were first observed in or determined to be extraterrestrial in the early part of the 19th century, and we still don't know what they are over 100 years later. Neutrinos were first detected coming from the sun in the 1960s, and then gravitational waves were detected for the first time in 2015. So all of these things contribute to a better and different understanding. So these new experiments which are going to be launched will be describing all of these. The optical observations, this is a very nice image which keeps on being updated. I think I downloaded this from Wikipedia, which shows some of the observatories. The ground-based one, here is the Extremely Large Telescope. And as you can see, it's going to be much bigger than all of these existing telescopes. And it's going to make a dramatic increase. Another interesting telescope is the LSST, that we'll now call the Vera Rubin Observatory, which will be a survey instrument. And we'll talk about that in a few more details later on. Here we see the James Webb Space Telescope and compare it to the Hubble Space Telescope. Notice how small the Hubble Space Telescope is, but the size of the telescope doesn't really matter. Gaia, for example, which we'll talk about, an important survey of distances, very small telescope. Kepler one, looking at Exoplanets, also very, very small. We had in David's introduction, he talked about Brian Harvey talking about collaborations between Russia in astronomy. We had a very good collaboration using this telescope, using the BTA, the Big Azimuthal Telescope, 6-meter telescope in Russia. And we observed our first optical pulsars using this instrument here. But the ones we're going to be talking about today will be the Vera Rubin telescope, the extremely large telescope, and the James Webb Space Telescope. One of the things which is going to happen is the way in which we observe is going to change. It's going to be less an individual astronomer going out, peering at his favorite or her favorite object. It's going to be the era of massive surveys and databases. This is where kind of deep computing comes in to analyze these massive surveys. I'll talk about Gaia in a second, which was plotting out, but the LSST, Large Synoptic Survey Telescope, will be a transient survey. And here is the LSST under construction. It's a picture I took when we were down using the Gemini telescope in 2020, just before the lockdown started. We were in Chile looking at this, worried about whether we would get back or not. And here you see the LSST under construction. As you can see, it's nowhere near finished because there's lots of holes in it. And here's a big crane, which is then used to make the dome. And these surveys here are basically designed to look at the whole cosmos. And in this case, the Southern Hemisphere. And in the LSST's case, it'll be taking 15-second observations with an 8-meter telescope, such that it will plot out and image the whole of the southern sky every 3 days and looking for transients. And this will result in an enormous wealth of information and new objects, which we can only dream of now. Gaia showed you how important this is going to be. And Gaia has mapped, it's a very small telescope, the position of 1.8 billion stars and produced a parallaxes of 1.5 billion. That's a significant fraction of the stars in our galaxy. The other thing is that's kind of an added bonus for this is that exact astrometry, i.e. where something is, can tell us about the presence of a companion. And this plot here shows you what happens. Most stars will be moving across the sky at a particular rate. And they won't move in a straight line because the Earth is going around the sun. So how the star moves gives us an indication of how far away it is. If it's a long way away, it won't move by very much. But if it's close to, its path will follow this kind of curved path here, which is shown in the dotted line moving around here. If there's a planet around it, it will also then move the star. So what we see is the big curved path is due to the Earth moving. The brown curved path is due to a planet around that star. So it's a way in which we can actually then observe a number of different planets around different stars. What we also see here is that sometimes stars will transit across the face of the star, and we'll see the brightness then change. So this was Gaia, and this is the map which Gaia produced, and what's been put here is the position and color as a dot of each star which has been found. And you can see this lovely map of the Milky Way with the dark bands of dark clouds, which will in the future be new star-forming regions. And we see here the Magellanic Clouds, this large Magellanic Cloud, small Magellanic Cloud. Here we see a globular cluster, 47 Tuc, down there. And if we compare that with the previous large-scale space survey, which is Hipparchus, this is what Hipparchus produced. And in 20 years, which is the distance between the two surveys, we went from this survey, to this incredible understanding. So it was quite a dramatic leap with what Gaia has produced, and it's still producing data. So the positions are still being refined. So this will produce more and more accurate maps. So here we have one experiment producing a publicly available database, which means that all astronomers across the world can now access this and use it for their own research. And this is one of the important new developments, is this kind of massive large-scale computing has enabled us to do this kind of work. The next one is the LSST, which has been called the Vera Rubins Observatory. And what is designed here, it's a very squat telescope. I'm just going to show an animation in a minute about its construction, which is under construction in Chile, on the edge of the Atacama Desert, in next to the Gemini South telescope. And it consists of a 8.4 meter telescope and a camera which can observe a very large 5.5 degree field of view of the sky, which is absolutely an enormous field of view. And it's going to basically take two 15-second exposures of the sky in different filters and then just chunk around the sky, and it generates terabytes of data every night, which then needs to be analyzed. So if you go to the LSST Observatory headquarters, it's basically a supercomputer center to actually handle these massive data sets and produce essentially a large number of catalogs which can then be used by all the astronomers in the world. And here we see a nice animation of it. Note when we go through that the difference between this animation and the ESO animation, which had engineers, were looking at the telescope, where here we appear to have accountants looking at the telescope, and this one seems to be standing 6 inches in the air, which is interesting. So we have maybe a different morality or something going on there. And its aim is to actually look at this. And here we see another accountant looking at the camera. And look at the scale of the camera here and the scale of the filters which are actually being used to do this. So basically, it's a fully automatic robotic telescope which will then be imaging the southern sky every night to try and get an idea for and looking for transients. So basically, it's looking for objects which change, and no doubt it's going to suddenly dramatically improve our understanding of transient and high time resolution astrophysics. And here we see more accountants looking at what's going on. And he's even bought his own briefcase, which is interesting. So this is the LSST, the Large Synoptic Survey Telescope. It's now named the Vera Rubins Telescope. In comparison, what we have is the ESO's Extremely Large Telescope, which is going to be the world's largest telescope. And here you can see the scale of it with people here. The mirror itself is 39 meters across. You can see the number of different individual mirror segments which are there. The secondary mirror here, is 4 meters across. So it's going to be the largest secondary mirror. And if you think of the William Herschel telescope, it's the same size as that, which used to be the third largest telescope in the world, is now just a component of this particular telescope. And basically, it weighs nearly 3,000 tons, and it will be moved. And what's actually quite alarming of these large telescopes, I've been in the Gemini telescope, which the mirror is much smaller, it's only 8 meters across. But you see this giant construction moving with no noise at all, because all the bearings are so friction-free. Its science objectives are going to be looking at exoplanets, galaxy evolution, evolution of galaxies in the early universe and the nearby universe, and cosmology and fundamental physics. And as I mentioned before, Nicholas Devaney's group is looking at MAURI, which is the adaptive optics system. Here we see a little image of I'll skip over this because I'm beginning to run slightly out of time. But it shows you the location of the Extremely Large Telescope in the Atacama Desert. It's worth noting that the mountaintop appears to be very flat, and that's because to make the telescope, the first thing they did was blow the top of the mountain off, which is quite a dramatic. launch of the telescope, and that was done about three years ago. And this indicates what's going to happen. This is the ELT cam, known as Mikado. It's going to observe it's an infrared telescope, the ELT primarily, mainly because it wants to look at early universe galaxies. And this is showing you what will happen when you have different levels of crowding. If you have 1 million stars per square arc second, which is a very small part of the sky, but it would actually map out a galaxy at the edge of the observable universe. With the HST, this is what we'd see, very little detail. With the JWST, which will be launched quite soon, a little bit more detail, but hopefully with the ELT and Mikado, we'll see a wealth of information and be able to resolve all of these stars. And then when we go down to fainter and fainter stars, then we'll be able to get, we'll still be able to resolve all of these stars here. The other aspect is this thing called the contrast requirement, 10 to the minus 4 at 100 milliards seconds and 10 to the minus 5 of 500 milliards seconds. What this is saying is that it should be able to observe some exoplanets directly, as long as they are sufficiently far away from their star. And this is indicating how bright a nearby object has to be. So it can actually get what's known as a very good contrast resolution. Harmony, which is a spectrograph, integral field spectrographs, and basically it takes 152 by 214 individual spectra. So you can actually then point the instrument at a galaxy and measure all the different spectra. And this is a very distant galaxy simulation, and this is what it looks like under the VLT with adaptive optics, and this is what it will look like under Harmony. So we'll be able to characterize all the individual stars in this galaxy near at quite significant distances. I'll skip over that. Next, that's the optical. And then what we have here on the ground is the next big project is the square kilometer array, which is exactly what it says on the tin. It's a radio telescope which has a surface area of 1 square kilometer. It's on 2 sites, one in South Africa and one in Australia, at different frequencies. And it's basically going to be looking at, again, the same kind of questions. How do galaxies evolve? It'll test general relativity in pulsars and black holes. We'll try and understand cosmic magnetism, which is an important aspect, very difficult to measure, hopefully through polarization. It'll study the first stars and black holes. And then another area, which gets a lot of people very excited, is it'll be looking for signals from extraterrestrial civilizations. And there'll also be unknown unknowns. We don't know. It'll be opening up a new vista into the universe. And we have Evan Keane, who's just come to Galway, used to be one of the project scientists from the SKA, and he'll still have links to this. And those people who've been to LOFAR would realize that radio telescopes quite often don't really look like telescopes. And here are the antennas of the low frequency array component of the LOFAR of the SKA. CTA is another one, high energy gamma rays through atmospheric Cherenkov. And here's something which looks a little bit more like normal telescopes. And basically it's looking for the interaction of charged particles or gamma rays with the upper atmosphere, which then produces a shower, an energetic shower of electrons, which can then be seen as a very, very brief flash of light. Currently, the Hess Observatory in South Africa, DIAS is a strong component in that, and as they will be with CTA, this is the next big European project. Again, it will be probably in Chile, and it will be then observing the southern sky and looking for high energy gamma rays coming from the southern sky using this technique of atmospheric Cherenkov, which happened to be what my PhD was on. And DIAS involvement through DCU, Irish involvement through DCU and DIAS, and this gives an indication of how it's going to be different. Here's the Large Magellanic Cloud, and Hess has managed to see 2 or 3 objects in there, whereas the CTA is expected to see a large number of different objects in there, and that will open up our understanding of the high energy gamma ray universe. And that will be looking at a large number of different areas where there are astrophysical shocks, pulsars being one type of object. Most peculiar telescope. I'd love to go to this one. I can't find a good excuse. This is the high energy neutrino observatory called IceCube, and this is what it looks like. It's in Antarctica, but it's just like an iceberg. Most of the interesting bits are underground, and what we see here is basically a large number of photomultipliers detecting light buried up to nearly 3 kilometers down in the ice. And what happens is that a neutrino will interact with the ice and produce a brief flash of light. Neutrinos are a fundamental particle which we have about 1 million billion neutrinos passing through us every second, day and night, coming from the sun. And even at night, when the sun has got, the neutrinos will pass straight through the Earth and then through us. So they're very difficult to detect. They very rarely interact with stuff like us. So to do this, you need a vast area of something which is clear, and then ice and water are used for this. And they will see a brief flash of light, and then from that, they can actually determine, you can determine the direction which neutrinos come from. And so far, it's a very difficult experiment to run, but at least one extra terrestrial neutrino has been discovered. A lot of them come from the atmosphere, but there's a lot which you can detect coming from a blazar. And a blazar in 2017, first extragalactic neutrino from a blazar was discovered by IceCube. And it's just an active galaxy, which shows these large jets of material coming out. And what happens is it's basically there's a black hole accretion disk, material flows out, and then material can get collimated up into a jet. And if you happen to be looking down the jet, you see some strange things, and you see what's known as a blazar. And it's thought that a neutrino was observed coming from being accelerated by this jet. So it's it opens up a new branch of astronomy looking for this. And hopefully in the future, maybe if gravitational waves detect the merger of two of these supermassive black holes, we will see neutrinos and gravitational waves and optical astronomy and gamma ray astronomy all observing the same object at the same time. Upcoming NASA missions include things like WFIRST, the Nancy Grace Raman Observatory. We also have the James Webb Space Telescope. I'm very excited by this one, the Imaging X-ray Polarimetry Explorer, because we take optical polarimetric observations, particularly of pulsars, with our GASP instrument. That will now be complemented by X-ray polarization. It's a very difficult thing to achieve, but there's a wonderful experiment going to be launched. And hopefully that will be launched sometime later on this year, in November the 17th, I think is the launch time. James Webb Space Telescope, we'll talk about in a second, and the Nancy Roman telescope, which is called WFIRST. This is basically a similar mirror to the Hubble Space Telescope, but has a very wide field of view. This little animation shows what's going on. I'm beginning to run out of time, coming up to an hour now, so I'll stop in a second. What we see, there's a field of view of the Egg Nebula, called Pillars of Creation, I think this image has been called. There's a ground-based image. The field of view of Hubble was this. The field of view of the Roman Space Telescope will be that. And this will allow large areas of the sky to be surveyed. And this will actually help our understanding of dark energy and dark matter, and also exoplanets as well, by effectively making surveys. Similar mirror to the Hubble Space Telescope, which are also similar to the size of mirrors used by the US military for their spy satellites, just because. James Webb Space Telescope will be launched. There's a link with DIAS. Tom Ray's group was involved in some of the infrared filters, which were going to be used on one of the instruments. It's mainly an infrared observatory. The next one, the Imaging X-ray Polarimetry, which we talked about, launched in November. And it's looking at the magnetic fields of magnetars, which have these very strong magnetic fields. And what I'm interested in is finding the mechanism for X-ray production in pulsars, both isolating and accreting, and their geometry, and that will actually probably help solve the problem of how do pulsars work. And again, also how particles are accelerating pulsar wind nebulae, which maybe will begin to address the cosmic ray problem. ESA, and it's important here to note that Ireland's a member of ESA, so these are our telescopes. And we have Irish involvement in both LISA and Ariel. And these are some of the telescopes which have already been launched. We've had UCD had a large input to Integral. We've been using Integral to observe the Crab pulsar, looking for polarization in gamma rays. Also the HST, ESA makes a large contribution to the James Webb Space Telescope, and Gaia was an ESA instrument. Two really interesting ones coming up are Athena in the early 30s and LISA in the mid-30s, which is basically this gravitational wave. It's basically 3 spacecraft separated by 2.5 million kilometers, and it'll be a gravitational wave detector. The current gravitational wave detector have interferometer arms which are a few kilometers long. This will be 2.5 million kilometers, and it will be far more sensitive. There's been a pathfinder to show that the technology will work. Now all they have to do is to create this, which is going to be an exceptionally difficult. And we'll be able to look at mergers of supermassive black holes, white dwarf binaries in the Milky Way, and stellar origin black holes falling into supermassive black holes. All these kind of very energetic, interesting events which are going to be done. Similarly, Athena X-ray telescope, which will be looking at the center of galaxies, including the one at the center of our own galaxy. Hot gas in the cosmic rays. Look at the energetic universe, and then random high-energy astrophysical events will be looked at as well. Euclid is going to be launched in 2022, and it's looking for dark matter. This is meant to be a movie. Yes, it is a movie. And it's basically answering the question, what is dark matter? What is dark energy? Sorry about the music. What is gravitational lensing? And what are baryonic acoustic oscillations? These are basically remnants of the early stage of the universe. It's basically sound waves, if you like, which shows you what's going on. I want to show this movie because it shows that without dark matter, galaxies would rotate differently to the way in which they do. And this is designed to essentially look at what's happening with dark matter. And basically, there'll be a general observatory as well. So there'll be lots of different ways in which we can actually begin to examine what's going on. Also looking at gravitational lensing, and this is where a piece of matter distorts space, and many of these have been able to see. So basically, we're looking at the signature of dark matter by looking at how galaxies are looking. This music gets more and more dramatic, so we'll go up to the next one. Athena, launched in 2031. We talked about this just now. Supermassive black holes explore the high energy events such as supernova explosion, energetic stellar flares. I haven't been talking so much about planetary missions. There are a number coming from ESO, Plato and Ariel, launch in 2029. I think Plato slightly earlier than this. And it's basically what we want to do is to look for Earth-like planets. And Ariel, very exciting, will be looking at the atmosphere. And again, I think Tom Ray's group in DIAS had responsibility for some of the filters for this. So trying to find out whether there's life, what you need to do is say what the atmosphere is made out of. And that's what Ariel will be looking for. So what we want to do is look at the atmosphere, how much water, and what is the radius, and that will tell us whether it's suitable for life like ours. I'm not going to talk about too much about the planetary missions. There's many of them, but I will mention in passing, which is not on this. JUICE will be launched in 2022. We'll get to Jupiter in 2029, I think it is. There are a lot of missions going to Mars. But I think at the beginning, David mentioned the Juno mission. It's worth going to the Juno website because there are some wonderful images of Ganymede, which it flew by in June, which is worth looking at. Search for life in the solar system. There's this lovely mission called Lucy, which is going to be launched in October. I really like this one because it's going on this incredibly weird path, which is to look at the Trojan satellites around Jupiter and Trojan asteroids, which are in this stable region 60 degrees away from Jupiter. And it's going on this strange path, which, if you look at it, goes up here, goes through these Trojan satellites, it comes back again, goes up through these, and so on. It's a mad mission, really. And 2026, watch this space, helicopter to Titan, satellite around Saturn, which will get there in the early 2030s. It'll be a helicopter. It's a drone, which will then fly and move around Titan, effectively looking to see what the conditions are. And Titan's been described as being the early Earth and deep freeze. JUICE, Jupiter's icy moons, is basically going to be looking at the icy moons which are around like Europa and Ganymede around Jupiter. And there's DART and Hera, which are asteroid impacts. These are designed to see if we can actually, this is NASA and this is ESA. Basically, one of the things which could wipe out life on Earth would be a large asteroid hitting us. And here is an attempt to try and see if we could move an asteroid if our technology. So basically something large and heavy is going to bang into an asteroid and then see how much it actually moves. There'll be other aspects of it. Looking at the ejector which comes out will tell us what the asteroid is also made out of. Who can take part in these? And I think it's an important message I'd like to say is that today's Leaving Cert students could be working on any of these missions. And Irish scientists have gone out and been working on virtually all of these different programs, and particularly the ESA ones and the European Southern Observatory ones, where we've already got a station of LOFAR here. And we have scientists involved in Euclid, JWST, LISA, ELT, and so on. And there's many more which I have mentioned. Scientists been involved in previous ones here. Some nice animations I downloaded from Wikipedia showing the LISA 3 spacecraft traveling around, following along from the Earth and detecting its gravitational wave. So what happens is the gravitational wave comes along and the distance between these two satellites moves by a very, very small amount. I've got these websites which I'm happy to copy and then send on to people that can actually have a look at this information. And I'm finished. Any questions? I overshot by time, so I apologize for that.
Well, that was amazing, Andy. Thank you very much for an incredible overview of all the discoveries to come.
Yeah,
making me panic because we're going to have to cover all this in the pages of Astronomy Ireland magazine.
You are, and also there are many more than this, unfortunately.
Yeah, I was listening to you say about all the missions to explore the solar system. That sounds like your next talk.
Yes.
Well, I'm not seeing many questions in the, or am I seeing questions? Yep. I'm going to let Laura handle the questions because she's been monitoring those. I might just jump in and throw in one of my own while she's getting ready to go. One is that, you know, we had in the 1940s the Hale 5-meter telescope. Then you were lucky enough to work with the Russians on the 6-meter. And then there were some 8-meter telescopes came up and 1 or 2 10-meter telescopes. Things more or less stop there. And the next jump is this 39-meter that Europe's building. And also the Americans trying to build their 30-meter. Why was there such a big jump, do you think, from sort of 10 up to 40?
Good question. We were actually involved in a project called the Euro 50, which is meant to be a 50-meter telescope, with the University of Lund. The jump was basically impatience. There were lots of arguments when the ELT was being designed, which was initially came out of the Euro 50 project. It was going to be 50 meters and then it was going to be smaller. That maybe it'd be more sensible to go to something which is nearer the American 30-meter telescope. But But it was decided the technology was there, and particularly because the idea of segmented telescopes, like you can see here with the James Webb Space Telescope, of individual hexagonal components, would have contributed to the potential success of this. So it was thought that you don't need a monolithic mirror. You can go up to something which is now 39 meters across. You're using a lot of smaller mirrors. So it's the technology which then allowed it.
Over to you, Laura.
Can I just answer one question here? I noticed that Leo Enright made a point, which I would like to comment, is that the CTA, the Great Trevor Weeks, would love it. Yeah, he Irish astronomer who helped develop gamma ray astronomy, high energy gamma ray astronomy in the 60s and beyond. He was also my external examiner for my PhD, one of the external examiners. So yeah, and sadly he died a few years ago. Anyway, apart from that, do you want me to go through the questions as they come through?
Yeah, so Emma Meehan asks, thank you for the wonderful talk, Andy. What do you think are the greatest computing and data processing challenges for the LSST?
It'll be the storage and then giving everybody access to it. As I said, there's basically a supercomputing center essentially attached to LSST. And what they have to do is an enormous amount of image processing to firstly get all those images available to people, then to begin to catalog them, and to then using AI techniques to begin to identify those ones which are showing transient phenomena. So every night, you want to do this as quickly as possible. And that's the problem, is you want to make sure a transient event is something like a merger, and that it's fast, and that means that it's going to require other telescopes to look at it also very quickly. So you need to do this processing extremely quickly. So what you want to do is to actually have this kind of real-time aspect to it. So the answer to it is the greatest challenge is to try and get to near real-time data analysis of the images. They're all images, so that makes it slightly easier. So it's not spectral, which you have to then reduce. But it's doing the image processing, looking for differences between that patch of the sky now and the patch of the sky yesterday. And you have to allow for the fact that the sky conditions will change and all of those aspects. So they were all combined together. It's an immense challenge.
Sorry, Laura, just might jump in there. Just for anyone listening in, we'll tell you briefly about the Perseids in a few minutes, take one or two more questions. But about the data processing requirements, is it true to say that the LSST, the Vera Rubin Observatory now, that you couldn't transfer all of its, I think there are 2,000 megapixel pictures it takes each time over the internet? There's not enough bandwidth on the whole internet?
Oh, you couldn't transfer the whole lot, but every night the data is then transferred down from the observatory summit down to the headquarters in La Serena. So they have their own fiber connection to do that.
Wow. Go ahead, Laura.
Okay. Edward Mullarkey asks, do many observatory contractors go bust?
I wasn't being serious about the accountants. They just look like accountants, particularly the ones hovering in the air. Do many observatory contractors go bust? Very few. Is the serious question to that is that, and mainly because there's so many checks and balances on who's doing the contracting beforehand. There have been examples of people going bust, but it doesn't happen very often. Any problems if local governments become unstable or unfriendly? Yes. One of the conditions when you actually put a telescope somewhere is you want to make sure that not only is it geologically stable, but it's also politically stable. The best astronomical site, apart from Antarctica, is probably somewhere in Kazakhstan. But it's regarded as too difficult to get to and potentially politically not necessarily as stable as it should be, or unfriendly. Now, unfriendly, unlikely, because there is general cooperation across astronomy. There isn't a, you can see that with the International Space Station that Russia and America might be at loggerheads, but they're not when it comes to space.
Leo Enright. Leo asks, what are the end member theories for dark energy matter? What explanations are possible? The worst and the best.
Everything, the worst blows everything sky high. That's true. One of the problems with dark energy, there's something called vacuum energy. And this is which is thought to be an explanation for dark energy. Now, the problem with this is that the best theories of physics at the moment predicts that dark energy should be, if that was the explanation of vacuum energy, about 10 to the power of 100 stronger than it actually is. And that's probably what he means by blow everything sky high, if that was the case. Or modern physics needs a little bit of a kick. That you've got here, we're on a cusp. And it's always interesting when you've got a problem which you don't understand, is what solution would come up. And if we think about what was happening at the end of the 19th century with the Nicholson-Morley experiment, where it seemed that the speed of light was constant. And what it took to explain that was Einstein's special theory of relativity, that in fact that it was, and that everything else then had to give, like space and time and so on. It's when you've got something you don't understand, new and interesting things can then happen.
We have time for maybe one more, Laura.
Yeah, so Chris asks, how much of an effect or impact will Starlinks have on Earth-based observations? Okay,
I really don't want to get started on this because my language might deteriorate very rapidly. I'm not very keen on these massive constellation of satellites, because when you take an observation, you're talking about, with a large telescope, you're talking about a very small field of view, but you're also talking about something which is very sensitive. And a long exposure could be completely ruined by a satellite passing in front of you, and it would, it could completely drown out because the glint from a satellite would be quite large, the observations you're making. So, yeah, most astronomers really don't like the idea of these Starlink type observations. They'll have a massive effect. And obviously the way around that is going to space, but that costs an enormous amount of money. I feel the same way about Starlink as I do about billionaires going to space. I'm not really in favor of it. But that's my problem.
That might be a good place to leave it. There aren't any more questions, Laura, are there?
Oh, yes, there is. What do you think?
There's just one.
Go ahead.
What do you think astronomy will be like in 100 years' time?
I think it will be quite incredible. And I think what will be is that we would have probably fully explored the whole of the solar system with probes going everywhere. There is an interesting development going on at the moment. There's a very nice mission, I could put a link to this, of a fusion-powered probe to Pluto, which will only take 4 years to get there, which is roughly technologically ready now. It needs a little bit of will to do that. And then that would provide the power for say, a lander onto Pluto. That is probably the future, is experiments like that. There is ESA have just published a kind of missions which will be launched in 2050, so it's in 30 years' time. And there's some very exciting, primarily a lot of very exciting planetary missions which are there. I would imagine there would be observatories on the far side of the moon, which would then be free from all Earth contamination, both optical and radio. So I would imagine it'll be in space. And I would hope the gravitational wave neutrino astronomy will be in its prime at that point. But who knows? Hopefully we'll all be here, or our descendants will be.
It's amazing if you think back to 1921 and where we were, and the fact that there's so much more technology and humans, therefore scientists,
Yes.
and better educated as well, I'm sure, on the planet. Speculating 100 years in the future, who knows?
It'll be, and also the impact of Chinese astronomy, which is coming in big time at the moment. It's making a massive impact. I haven't mentioned some of their developments, like the Big Radio Telescope and some of their satellites. They will have an increasingly important impact on our understanding.
It's very exciting time. So all I do, Andy, is thank you enormously for a superb talk. Covered so much. I think I'll probably watch it again. Because you don't realize when you're just picking these things up piecemeal how long the list is of all these missions and instruments we have and the discoveries they're all going to make. Certainly a very exciting time. I'm even more excited now than I usually am about the future of astronomy. So a huge thank you, Andy, and hopefully we'll have you talk again soon.
Absolute pleasure, and I hope it would be in person rather than by this strange technology, because it's much better to see people than to be in the same room as them.
Absolutely. Let's hope so. Okay, well, what we're going to do is just briefly tell you what's in the sky and then about our next lecture, because we want to tell you a bit about the Perseids, because we've changed our mind about the Perseids. Most of what I'm going to say is in the magazine. If you get the magazine, you've already got the diagrams. Briefly, what planets are on view? Well, Jupiter and Saturn are at opposition this month, which means they're at their very best. I managed to get a glimpse of through the clouds last night, blazing away. Saturn looks superb if you have a telescope to see its rings. There's details of seeing the great red spot and some of the moon events on Jupiter in the magazine as well. If you like looking very low in the west, there's a good reason to do it tomorrow and Wednesday. As you'll see on page 26 of your magazine, we have a diagram that shows the moon will be quite close to Venus. So Venus will be low down, but the moon signposting will actually make it easier to see. And I think the weather forecast for tomorrow in particular is not bad. So be ready soon after sunset. Read up on the information tonight so you're ready to see Venus near the moon. The moon will be a very thin crescent, so the dark side should be glowing with earthshine. It's going to be a spectacular sight to the naked eye. If you've got a pair of binoculars, even better. And I think even smartphone cameras should be able to record this well. So be ready and check it all in the magazine. Have a look at that, both tomorrow, Tuesday, and Wednesday, as the details in the magazine. Jupiter and Saturn we've covered. They're now, because they're in opposition, they're visible all night long. They rise at sunset and set at sunrise. So that couldn't be easy to tell you when to go out and see those. They're going to get close to the moon on Friday, August the 20th. So that's next Friday. That's Saturn, Friday the 20th of August. And 21st, the night after, Jupiter's close to the moon. There's a diagram in the magazine showing you that. Looking ahead, our next lecture is on the 13th of September. And on the 9th, the Thursday before that, Venus will be near the moon again. But there'll be more of that in your September magazine. That'll be out at the end of August. International Space Station, I said, is not really visible. There are some Starlink satellites around. There are terrible vermin in the sky. They've already ruined one of my photographs in particular. And but they do look very pretty shortly after launch. If only they would just go away after that. We'll keep you posted on social media about International Space Station Starlink visibility. There's supposed to be a launch, I thought, this week, but I couldn't find the exact details of it. They might be postponing it for a while. We'll announce it on social media as soon as we find out. We also been mentioned in the weekly emails as a nova in Cassiopeia that peaked to naked eye visibility twice. It's been bouncing up and down in brightness. I've never seen anything like it. Just checked it this evening. It dropped dramatically. It came up a little bit and it's dropped again. Who knows with this nova Cassiopeia? We haven't had many sunspots around and therefore not many predictions of the aurora, but we are heading towards solar maximum now, so you can expect more activity there. And if we get an aurora alert, we'll post that on our social media as well. So I've kept the best to last, the Perseids. There's a full article in the magazine, a full page, giving you some ideas of how to observe it there on page 29. So hopefully you've all got that. Briefly, the maximum is on Thursday this week, the 12th of August. But it's in the early evening from Ireland. And what that means is if you're watching early on Thursday morning, i.e. stay up late on Wednesday night, you actually will see a very large number of Perseids as well. And we've been looking at the graphs of how the activity of the Perseids proceeds over time. And it seems that there are more Perseids before maximum than there are after. So that means that actually when Thursday morning, Wednesday night, could be as good as Thursday evening. So try to stay up late on Wednesday night into Thursday morning, and definitely watch on Thursday evening as soon as it gets dark, and tell us what you see. On our website and in the magazine, you'll see we're trying to do a national Perseid watch, and all we want people to do is count how many they see every 15 minutes and email it as soon as you're done that night if you can, first thing the next morning otherwise. And it's very simple. You might say 11 to 11:15, I saw 12. 11:15 to midnight, I saw 22. Whatever it is, give us your location as well, and those reports will appear in the magazine. And that has scientific use, because by monitoring the progress of these showers by the general public, that we've actually been able to tell when they peak, and something you can contribute to as well. You might get bitten by the bug of meteor observing. And I think it's 2015 is the last time that the Perseids were moon free. There'll be no moon in the sky to brighten it up. So those of you who have dark rural skies are in for a treat if the sky's clear. Don't believe the weather forecast. The cloud cover is the hardest thing to predict. It can vary from kilometre to kilometre in Ireland, and 10 minutes to 10 minutes as well. So just be ready, keep a vigil, even if there's a lot of cloud forecast. You can often go to bed and find out then it's cleared up and you missed a fantastic show. So that's the Perseids. They'll appear anywhere in the sky. It's known for producing a high proportion of fireballs, really bright meteors. So it's quite spectacular. You might see, I've seen over one a minute in the last few years. Hopefully you'll get rates like that. More in the magazine. That's everything that's happening in the sky. Let me just tell you about a couple of events coming up. Just a reminder, Andy mentioned the Juno mission. It's in orbit about Jupiter, sent back those lovely pictures of Ganymede in particular. And you can hear all about the Juno mission on BBC 4, 11:50 p.m. on the Sky at Night. Our Starbecue is set for September 4th. We'll have to let you know the next meeting whether it went ahead or not, but follow our social media. If we get permission to go ahead, we certainly will. And the evening classes that I said we run, they start on October, which you can enroll now. Just go along to the website, astronomy.ie, and sign up. The next lecture is on September the 13th. Remember I said the second Monday of each month. It's been given by James Fradgley, and he's going to talk about a fascinating subject, life in the universe. Are the aliens really there? If you take a look at the website, read the description of the talk itself, you'll see he's going to cover all the aspects of how life got started on the Earth, because we want to know about intelligent life in particular. A lot of people believe simple life should be teeming in the universe, but does it ever become intelligent? There's a lot of work's been done on this, and we have one example, us, here on this planet, and so it'll be a fantastic roundup of that. I'm really looking forward to that talk, because we get asked so many questions about it all the time. You can book your tickets online now. As I said, don't forget to follow us on social media as well. If you're not a member, just go to astronomy.ie and join up. You've heard what Andy's told you this evening. We're going to be covering all that in the next 30 years of Astronomy Ireland. So that's the formalities brought to a close. If anyone wants to stay on to have a brief chat for a few minutes, we'll take any questions. You can actually turn your audio on and just shout them out. So thanks to all the volunteers who helped run the meeting tonight, and a big special thanks to Professor Andy Shearer